All right, good evening, good morning. We're going to continue with our Calc 2 discussion here. So we're going to begin on chapter 8, okay, which is a techniques of integration and some applications of integration. Okay, so the first thing we're going to learn here, let me go ahead and share my screen. Okay, the first thing we're going to learn is something called integration by parts. This is the next integration technique that you get to learn. You probably won't learn too many more of them. Okay, the engineering class learns quite a few because they have more functions to deal with. And I wish we actually did do some more, but this is what we have. Okay, let me not go with that first yet. Okay, so if you reviewed, you should remember chapter 4. We talked about techniques of taking derivatives. Okay, one of the things we talked about was how do you take the derivative of a product, right? So what if you have something like the square root of like x cubed plus 1, right, times say ln x. Just to make things really interesting. And I want to take the derivative of this. Okay, so usually what we do is we call this u, we call this v, okay? And because these are times between them, in order to deal with this, right, we had to take the derivative of this product, u times v. So the way I memorize this, and you do have to memorize this, I'm sorry, is derivative of the first times the second plus the first times the derivative of the second, okay? So the idea is that, and this is the image I always have in my head when I do this. I don't know how you guys do Christmas, or even if you do Christmas. If you do, great. If you don't, that's fine too. Was we had different, I'm the oldest. My brother and sister were all separated by about 2 years. So when it got old, when it got time, like when my brother and my sister had reached like the age that I'd done when we started setting this up, we all took turns. Like every year we would switch who got to do what. And we had all these, my mom was like really into Christmas presents or Christmas ornaments. So we had a few Christmas ornaments that had the little, some assembly required part to that, okay? So the oldest son went first. Next year my brother went. The year after that my sister went, and we just rotated it. So each time, like you'd have like a little box that your Christmas ornament was in, and it was up to you to like figure out how to put it together. Okay, so that's my derivatives. Okay, so for me, the whole point or the whole idea of doing the derivatives is that you have the little pieces, you put each one in their little box, and you work on each one of them until you can put the whole thing together. Okay, so for me, like doing it this way of kind of separating them out into each little box so you can assemble the whole derivative, that's what we're doing. Okay, so this derivative here, right, this is x cubed plus 1 to the 1/2. So the derivative here, right, this is 1/2 x cubed plus 1, dang it, to the negative 1/2, right, that's 1/2 minus 1. But then there's a chain rule inside here, which we have to take the derivative of this part, okay? So we have the 3x squared here, okay? So that's one box, okay, times v, that's just natural log of x, okay? Plus, and then we have our first one, so this is x cubed plus 1 to the 1/2 power, and we have the derivative of natural log x, which is just 1 over x. And then you put all this together, okay, and that would be your derivative. Okay, so we'd have what? We'd have 3/2 x squared divided by or times, it's up to you, cubed plus 1 to the negative 1/2 times natural log x. Okay, and then here we'd have x cubed plus 1 to the 1/2 over x. Okay, and that would be our derivative. So we're going to go backwards. Okay, I'm not going to go backwards with this problem because this is a little messy. Okay, we're going to start off with something easier. But the idea here is if you had the derivative of u v, this was equal to what? This was equal to, let's go ahead and say this is equal to u tick v, okay, plus u v tick. That's what we just did, okay? Now, what I'm going to do is I'm going to take my uv tick, right? That's going to be uv tick is equal to the derivative of uv minus, right, u tick v. Okay, all I did was take this to the other side, and I just swapped the order. Okay, so we're just reading this from right to left instead of left to right. Okay, so UV, that's positive, and we have derivative of UV minus, and I'm just going to put this on the other side, U tick V. Now, let's integrate both sides here. So we have U V tick. Okay, so the derivative, so I'm going to write it this way. Okay, so it's U times the derivative of V, so I'm going to write it this way. Okay, is equal to, what do I get when I integrate the derivative of UV? We just get UV, don't we? So the integral of a derivative minus, and then we have the integral of U tick V. All right, so that's what we're doing here. All right, did I get this in the right order? No, I wanted it in the other order. So no, I didn't. I got it right. Okay, VTO. This is what we want. And we're going to change this out. Okay, so instead of U tick, we're going to have du. Okay, so V du, U dv, and then the V UV in the middle. All right. This is the formula for integration by parts. Okay, now I would recommend not memorizing this formula because I'm going to show a slightly easier way to get done. Okay, so what we're going to do is we're just going to make a box. We're going to say U equals du equals, and then we have dv equals, and then integrate, we get v. So whatever u is, we'll write that down. Then we take the derivative of it. Here, right, we set down what v is. Notice, here's my u, here's my dv, here's my u, here's my dv. All right. So we took this part, we made the top part of our box this thing, okay? And then what we're going to do is we're going to integrate this. So to integrate, what we're going to do, okay, is we're going to multiply UV together, that's here, okay, minus V du, which is this part here. So if long as you remember, like, oh, I have to make a little box, you're going to be fine. Okay, just follow this as a diagonal and then cross back. Okay, that's how I remember my integration by parts formula. I've never memorized this formula. Okay, I always have to work through it once, and because I never remember which side which one is on, I always have to kind of work it out because I don't want to mess up in front of you. Okay, but when it comes down to like the actual doing of it, it's u du. That's what you're setting up. Okay, from your values. And then once you've got that, you just take the derivative over here, you take the integral over here, cross, move over, there's your integration. Okay, so I would not memorize a formula, I would just kind of memorize the pattern. Okay, it's a diagonal and then sweep back. And that's our formula. Okay, so we know the derivative of the natural log is equal to 1 over x, don't we? So, but you have not learned what the integral of natural log x dx is. Okay, so there's like the canonical reason why you would learn this, because this does not have a nice form. Okay, this is 1 over x, but this one, go backwards, I don't know what it is. Okay, so what we're going to do is we're going to break this into 2 parts. I don't see 2 parts. That's why this is a tricky one. There's 1, there's 2. So we're going to say u equals natural log x, dv equals dx. All right, just like we had up here, right? U dv. Now we're going to take the derivative of natural log x. Okay, so du here, we know the derivative. The derivative is 1 over x. It's not too bad. What is the integral of v, or dv rather? So the integral of dv, right, is just v. What's the integral of x? Or dx rather, it's just x. So what we're going to do next, now that we have our box set up, okay, is we're going to go ahead and we're going to say u dv minus v du, okay, or uv minus v du. Okay, so let's go ahead and write that down and see what it looks like. Okay, so this is x, outline x, right, x times natural log x, minus the integral. See, we do our value here. We couldn't really integrate this because we didn't know what functions they were, but now we're going to go ahead and integrate this. Okay, so this is 1 over x times x. Okay, so integrating this cancels, right? X over x is just 1. It's just a dx sitting here. Okay, because of this one. I'll write this down. Okay, so our answer is going to be x ln x minus, right, integral of dx is x. Okay, and then what do we have? We have a plus constant. Okay, technically there was a constant here because we integrated. Technically there's a constant here because we integrated. So we would actually have a c1 plus c2, which is just a constant. Okay, and that is how you integrate natural log of x. Okay, when you are dealing with this integral, you might have a little u substitution going on here. This might require a u substitution. This might require other kinds of techniques of derivatives. There might be a chain rule in this, okay, etc. Now, the thing about the integration by parts is all the little puzzle pieces that you have here, they have to fit your problem exactly. Okay, so this was the integral of ln x dx. Notice there's a little box for the dx. Notice there's a little box for the ln x. So whatever you've picked here and here, these have to combine, excuse me, these have to combine exactly to fit this. Okay, there's no, kind of slick u substitution you could do to make something look a little bit different. You're not allowed to do that. Okay, you do this u substitution here, but you're not allowed to just start solving and playing around with u substitution the way you did in the previous chapter in order to get this. Okay, so they have to fit, like lock and key. They have to fit. The two puzzle pieces have to be perfect. Okay, u substitution, you're allowed to kind of mess around a little bit. Okay, and by that I mean if you had a x to the, say, x times the square root. Well, let's do it this way. Let's just do an x plus 7 or something, and we had that to the 5th power. You could go ahead and let your u equal x plus 7, right? And x would equal u minus 7, and du is equal to dx. So when we wanted to go ahead and take this derivative here, there would be, there could be u substitution here to do some things. Dx, right? Because the x could go back to be u minus 7. The u plus 7 would just be x to the 5th. We could, we could go ahead and distribute and integrate piece by piece there. So that's the deal with u substitution, where you're allowed to do something like this. Not allowed to do it with the integration by parts. Not really. Okay. So that is how to do integration by parts. Okay. The canonical problem. So usually what you're looking for, and you can look on YouTube to find other ways to integration by parts. You're going to come up with something called tabular integration. I hesitate to show anybody this because the last couple of times I showed students how to do this, this is the only technique they ever learned. It was completely wrong, but it didn't stop them from using it. It also didn't stop them from getting the wrong answer. So I would appreciate that you just did them like the box method rather than the tablature method. I generally don't give you problems that require like huge amounts of parts, because the thing about integration by parts is, notice there's an integral here. There could be another integration by parts inside of the integration by parts we've already done, and continues. Okay, the engineering calculus class, they get so many delightful problems where this happens over and over and over again. It's hard to find yours because you don't have trig functions. So if you do go online looking for it, there's like an order that you're supposed to generally guess. It's not always going to work. It's a rule of thumb. It's not this is a prescription for doing it. Okay. Yeah, you don't have quite so many formulas. You don't have quite so many functions to work with. You have polynomials, radicals, exponents, logarithms. Okay. So there's not a whole lot of things we could do. So you don't require quite as many. Remember that when you go to the YouTube thing and you're looking for it, you're like, what's an inverse trig function? like something you never have to deal with, and I'm not going to pull it out of a hat and say, here, you've never seen this before, deal with it. That's not happening. Okay. Your class specifically avoids doing the trig stuff. So if you see that, if you're following it, realize this is not your game. Okay. You don't have to deal with this. So we're going to talk about the ones that you're going to see in your class, in your book. We're not going to talk about like stuff that is way out of bounds because it's in a different class. Okay, so I just want you to realize like you're going to go looking and you're going to go see stuff that's like, I wish I didn't see that. That's what's going to happen. It's not that you can't look. It's not going to burn your head off like an Indiana Jones or something. It's going to be, you're going to look at it and say, oh, I see how this works. So stuff that you're going to see. Generally, a polynomial times an exponent or a polynomial times a logarithm. Okay, those are generally the two types of things that you're going to be dealing with. Okay, so we have integral of, okay, 9x e to the 8x, okay, dx. Now, when you're picking your u and you're picking your dv, okay, and just like u substitutions, you think, I'm always going to guess right. You are lying to yourself. You are not always going to guess the correct u. You're not always going to guess the correct dv. All right, it's going to change. So what I want you to do is realize like you might have to back up and make a different guess, and that's okay. It happens to everybody, right? So it's okay to say, oh, I made the wrong guess. I guess I should try a different one. Don't erase. You may have made the right guess, you just didn't recognize it yet. So I would just scratch it out or turn the page and move something else. Try a different guess. Okay, but you might have to reference this because your next guess might be looking terrible too. And you're like, oh, which is the least of my problems. Okay, so that's what you're doing. How do you pick? Well, we're going to take a derivative here. Okay, now if I'm going to take a derivative, which one of these functions, 9x or e to the 8x, which one gets smaller? By that I mean which has a lesser power, which has a derivative you can take very easily. So both of them are pretty easy derivatives, so that doesn't help. But the 9x, if I take the derivative of 9x, I just get 9. It's getting smaller, okay? So we want u to be 9x, because when we take our derivative, du equals 9 dx. Notice there's no more x term, right? If I had to do this with a quadratic, we would go from an x squared down to an x, down to a constant, okay? If I had to do it for an x to the fourth, we'd have x to the fourth at first, take derivatives, we're going to have x cubed, x squared, x, and then down to a constant. So it's getting smaller. That's what I mean by smaller. Integral or derivative, e to the x, if I take the derivative, it's the same. It's an easy derivative. If I take the integral, it's an easy derivative. Okay, so this is a safe choice for it. You could put this anywhere you wanted to. It's always a safe choice. Okay, so my dv, e to the 8x dx. Okay, now we got to integrate this. And you might be tempted to do this, and it's fine. Okay, nobody's going to come back to you and say, hey, I noticed you did this by integration by parts. You should be further advanced by this. No, you shouldn't. We can say let u equals 8x, du equals 8 dx. So when I go to say this is e to the u, right, because u is 8x, and then I've got a dx equals du over 8 here. So we have a little bit more room. Okay, so we're going to have 1 over 8 integral e to the u du. What is that integral? Well, that is the integral, sorry. That is 1 over 8 e to the u, or e to the 8x. Okay, let's go change that back into an 8x here. Okay, again, there's a formula you can memorize for this, and that's fine. If you did, fantastic. If you didn't, here's your workaround. Okay, so I'm going to go ahead and put this together here, right? So this is u times v, okay, times v du. Okay, so we have 9 over 8, so 9/8, and then we have this x e to the 8x minus, right, minus integral of 9 over 8, it's this 8, that's 9, okay, e to the 8x dx. Okay, let's clean this up a little bit. So we're going to have 9/8 x e to the 8x, okay, minus, I'm just going to pull this across, 9/8 integral e to the 8x, okay, to the 8x dx. Now, if I didn't know any better, I could have sworn I integrated, right? I could have sworn we integrated e to the 8x one time before, okay? So we're just going to kind of like, oh, look at that. We already have this written down. So we're just going to write down 9/8. That's this one, x e to the 8x minus, and then here we have 9/8 times, what was my integral of e to the 8x? It was 1/8 e to the 8x times 1/8 e to the 8x plus c. So here we go. We have our answer of 9/8 x e to the 8x minus 8 times 8 is what? That's 64 e to the 8x plus c, and that is our answer. Okay. I put in a couple extra steps. Okay, I took my time with doing this. It's not quite, you didn't have to quite do so many steps or so many lines that I did. Okay, and as you do more, you'll get better. Okay, but that is how you do integration by parts. Okay, so this is what this is: 9/8 x e to the 8x. Okay, is it plus or minus on that one? Did I put? It's a minus, so that's 9/64. 9/64 e to the 8x. Okay, and I believe there was just a plus c after that. Okay. Some books tell you like which constant of integration to use. Yours doesn't, so it just always assumes c, I believe. But there we are. All right. Check. Oh, here, my mistake right here. I even said it. We're going to check our sign, and I completely blew it off. Okay, there we go. So that's integration by parts for that. Check your signs. Okay. This is also a very canonical problem. Okay, so let's go see if there's a closer one here. Not quite so. Nah, if you ever have to do a natural log one, if you see natural log, integral of natural log, you're almost always guaranteed you're going to use integration by parts. Okay, not always, but mostly. Okay, I'm going to pick this one because it's got an x, natural log 7x. Okay, so what are we going to have here? We're going to have integral of 8x times ln of 7x. We're going to specify that our x is greater than 0, so we don't have to divide this thing up into two pieces and work on that. Okay, so let u. Well, okay, the last one we said 8x is a good choice for this to get smaller, but can we take the integral of just natural log x by itself without pulling anything away? Like, no, you need integration by parts to do this in general. But we do know the derivative of this, don't we? So we're going to say u is equal to natural log 7x. dv is equal to 8x. Okay. So when we take the derivative of this, right? Derivative, this is 1/7x, right? 1/u du. But we need a chain rule. What is the chain of 7x? What's the derivative of 7x? It's just 7. Okay. V is going to be, just take the integral of 8x, right? That's 8x squared over 2, isn't it? Right? We have a dx here. So we'll clean this up a little bit. So our du, right, is equal to the 7's cancel. That's 1/x dx. Okay. And then v is just equal to 4x squared. Okay. So it's a little bit larger of a box here, but it's not gonna worry us too much. Right. So it's just going to be uv, right, minus v du. All right. So when I go to write this thing down, okay, we're going to have uv. So this is 4x squared times natural log of 7x. Okay, minus integral. I don't want to get too close to the side here because it blinks on and off more. Okay, minus v du. So this is 4x squared times 1 over x dx. Okay, so let's go ahead and write this down over. Let's feel a bit safer. So we're going to have, what was this, 4x squared? 4x squared ln 7x minus, okay, integral of 4, what's x squared over x, right? Does that make sense that this would just be x dx here? So instead of doing it this way, I'm just going to say, well, x squared over x is just x. So we're going to knock that out for a moment. Okay, just have to integrate 4x. So this is 4x squared ln 7x. This is going to be minus 4x squared over 2 plus c. So we have 4x squared natural log 7x minus 4 over 2 is 2. 2x squared plus c. And that is our integral for, what do we start with? 8x times natural log 7x. Okay, so this is going to be 4x squared natural log 7x. All right, minus, and then it looks like, what are we going to have here? 2x squared. 2x squared, okay, and then plus our c, and then we're going to go. Nice. Okay, so that's pretty much what we're dealing with. Okay, when you have to do a definite integral, it's going to be on both of the terms here. Okay, both. So let's see here. Let's try 5, I think. Let's take a look at what 6 is. Yeah, let's do 6. This looks a little bit difficult here. All right. So there's a couple of ways to do this one. Okay. One of them would be the technique we learned from the last time with the U substitution. This is going to be a integration by parts problem, but either way. So this is 4x squared times the square root x plus 5. You don't need integration by parts to do this one because we can always say let u equals x plus 5. Okay. If we say this is x is equal to u minus 5, and then we have x squared here, so we would say x squared equals u minus 5 squared. Okay, so we could integrate instead 4x squared, this is u minus 5 squared times u, that's x plus 5, and then we could go about it that way. So you didn't need to use integration by parts here, okay, but we could, but we're going to. Okay, so in this one, okay, we have integral of 4x squared root x plus 5 all dx. So we're going to have u equals and dv equals. Well, this one is kind of a pain to differentiate or integrate, okay? But this would be x plus 5. And if I take the derivative, right, we have 1/2 x plus 5 to the 1/2 negative. I don't want to deal with that in my du to deal with it even more. Okay, so it's just going to get uglier and uglier. It's going to stay as a fraction. Okay, generally, if you have to do this problem twice, because you have integration by parts inside of an integration by parts, you generally want your, whatever you pick for your u, whatever you pick for your dv, pretty much has to be like the same kind of term. Okay. So let's let u equal 4x squared and let x plus 5 to the 1/2 power be our dv. Okay, so this is dx here. So taking our derivative, right, du is equal to 8x. V is equal to, well, I've got to integrate this thing. Okay, like I said, it's not going to be fun either way. So this is x plus 5 raised to the 3/2, and then we have 2/3 out here. Okay. Looking to see whether or not doing it the other way around might be better. But we'd have a x plus 5, 1/2 x plus 5 raised to the -1/2, and then we'd have 4/3 x cubed here if we went the other way around. So this way you don't want to cross things out or erase it, because you could look at this and you say, oh, this looks terrible. Like, yeah, it does. Okay, so uv, so this is going to be 4 times 2 is 8. On the bottom we just have a 3, so here's my uv, x squared x plus 5 to the 3/2 minus integral. Okay, and here we have uv, so this is 8 times 2 is 16/3 x plus 5 raised to the 3/2. Okay, so this looks delightful, but I can put it off to the side because we never have to deal with that again. Okay, this looks less delightful, maybe more delightful. Again, we could use the technique that we learned in the previous chapter. Okay, but maybe you didn't see it. Guess what we have to do? We have a product, right? We have two functions times each other. I can't put this in there. So we're going to have to do integration by parts again. All right. So what I'm going to do is I'm going to put this aside. So this is 8/3 x squared x plus 5 to the 3/2 minus, okay, we're going to go ahead and let u equal 16/3 x. du will be 16/3. Okay, our horrible travel was almost over. Okay, dv, x plus 5 to the 3/2. Okay, let's integrate it. So we're going to have x plus 5, add 1, so that's going to be 5/2, and we're going to have 2/5 here. Okay, notice I put the coefficients, okay, with the x, so that I can make the problem a little smaller. Okay, so we go ahead and we multiply uv, so this is 1/3 x squared x plus 5 to the 3/2 minus, that's this minus, and then we need big parentheses, so we're going to have uv. Okay, so 16 times 2 is 32. 3 times 5 is 15. Okay, we have x plus 5 raised to the 5/2 power minus integral, and then v to u. So this is 16/3 times 2/5 x plus 5 raised to the 5/2. Okay, see how much fun that is? This does not need to be integrated again. So we're going to have 1/3 x squared x plus 5 to the 3/2 minus 32/15 x minus 5 to the 5/2 minus, oh, sorry, minus times a minus is a plus. Okay, 16 times 2, 32, 3 times 5 is 15. Okay, and now we just have to integrate x plus 5 to the 5/2. Okay, that's not so bad. There's a dx here. There's a dx here. So this is going to be x plus 5 raised to the 7/2. Then we have 2/7, 32 over 15. This looks great, doesn't it? Okay, so 32 times 2 is 64. 7 times 15 is 70 plus 35, so that's going to be 105. Okay. And then we have x plus 5 raised to the 7/2 plus c. And then what's going to happen here, these are just going to come down. So this is 32/15 x x plus 5 raised to the 5 halves minus, and then we have 1/3 x squared x plus 5 raised to the 7 halves. Okay. So those are our, oh, this is a 5 halves here, so don't let me mess that up again. Okay, so that is our 3 terms. Okay, x squared, x, none. And that would be our integral. Okay, there are other ways to do this problem. You're going to get an answer that's going to look different. If you multiply it all the way out, including this stuff, that's going to combine with our c, and we're going to have different c's for the different 2 problems that we've done. Okay, that's fine. So let's see what we have here. Okay, let's go. I don't want this. I don't care about that. I'm just trying to put this down so I only have one little thing to look at. We'll see what we have. All right. So here, what is this going to be? 1/3. Okay, I'm not going to even pretend that this is going to go in the right way, but who knows? We got lucky. This is x plus 5 raised to the 3 halves, right? Minus 32/15, okay, times x plus 5 raised to the 5 halves. Okay, minus there. Okay, and then plus 64 over 105. Oops, 105. Now we have x plus 5 raised to the, so what was that, 7 halves? 7 halves plus c. Okay, and that is yet another way to do this. Again, my first choice would have been the technique we learned in the previous one, but there we are. Where are we? Don't move me out of the way. Okay, so this should be, yeah, we'll just check our answer. Kind of interested in what I did wrong here. Oh, you know what? No. I did forget an 8. I forgot this. Oh, there it is. 4x squared. That would have been 8x. Okay. How's everything else doing? Yeah. So don't forget your first coefficient. All right. We're going to have to deal with that. But that's where we are. All right. Yeah. So I forgot this. Did I have that up there? Who knows? Beginning. I did, didn't I? Oh, I see. My 8 was squished into a 1. That's why I screwed up. Okay. All right. I guess penmanship counts here. All right. So that's that issue. All right. So yeah, I know. All right. Same idea. Okay. Let me see if I can find a. Oh, all right. Hold on for a second. We'll be okay with that. Okay. And yeah, all right. Let's go back to, oops, okay. So these problems, they're good to know, they're good to see. We had quite a bit of this kind of problem. Oh, I didn't want to do that. Can I control Z? No. Okay, when I went to school, we had quite a bit of problems that would do this. Okay, because we didn't have Desmos, we didn't have anything like that. Okay, so you have on your own to figure this out. Okay, this is actually one of the. If this was engineering calculus, I would just put that on there and say, "Good, best of luck, guys," because this is a form that they could do, but you need trigonometry to do it. Okay, so what do we have? We have We have integral of 9 over, not that it will be an easy problem. Okay, by no means would this be an easy problem. So 121 minus x squared. All right, and dx. All right. So we have that. And what we're going to do is we're just going to kind of snoop around and see if we could find something in the table of integrals. I'm going to start with page 1 because why not? Okay, so what we're looking for is something to match this one. So in the bottom, I want a square root, but I want a minus sign in there. So this is a x squared minus a squared, kinda. I would rather have a squared minus x squared. I like this one more, but we need a square root. Aha, look at this one. We have 1 over an a squared minus an x squared with a spare x out in front here. So number 9, the number 9 on the table, that's looking pretty good. Okay, so what we're going to have here is we're going to have 9. Okay, so in this case, right, a is equal to 11, because 11 squared is 121. And then our u, right, is just going to be our x. Okay, because these are usually given to us in terms of u's, but in this case, I guess not. Okay, because this get harder where this is a u squared and you have to deal with a dx in there and everything else. Okay, so we have negative 1 over a. So this is negative 1 over 11. Okay, negative 1 over a times the natural log. All right, and we need a 11 plus square root of 121, it's 11 squared, minus x squared, okay, all over x. Okay, this is where I'm looking at right here. Okay, and then plus c. Okay, so that's what we're looking for, something like that. Okay, I'm unlikely to give you one of these on a quiz, okay, because I have to give you a table of integrals to deal with. Okay, and I'm not just gonna say, well, you can look them up. I'm like, no, we're not doing that. Okay, but there we go. We could also use Simpson's rule to get an approximation if we had a definite integral here. See? So we learned that one. Okay, so we'll say done with this. Okay, so let's do one more of the hard ones. Okay, so the rate of growth. So a rate is already a derivative. Okay, the rate of growth from a micropopulation is given by mtic of t. That's our rate of growth, 34t e to the 2t. Okay, so we can go ahead and do this. What is it? 34t times e to the 2t. Okay, so this is y is equal to 34t times e to the 2t, so we can get an idea of what this is going to look like. Okay, so we have our, here's our 0. Okay, this is pretty much going straight up. Okay, so I guess this is a very viral bacteria strain here. Okay, so there we go. So just to see what it looked like. This one. Okay, what are we doing here? Okay, the total accumulated growth in 2 days. So what we're going to do is we are going to integrate this, the total growth, right? We're going to add stuff up from 0 to 2 for this many microbes. Okay. You kind of don't want to put a 0 in here, although it's over the first 2 days. Okay. I still want a an initial condition, but there we go. All right, so mtic is equal to 34t e to the 2t. 34t e to the 2t, right? So we have to integrate this. So we're going to integrate this from 0 to 2, 34t times e to the 2t. Notice I've got a polynomial thing times an exponential. That's a prime case for integration by parts. Okay, so we have let u is equal to 34t, du is equal to 34. Again, this is going to get smaller. E to the 2x, e to the 2t, it's just going to be unchanged. our dv is equal to e to the 2t dt. And then our v is going to be 1/2 e to the 2t. And all I'm doing here is I'm just kind of taking this derivative in my head. E to the 2t would be e to the 2t times my chain. So times 2. If I wanted to undo it, we would have this. Okay. So there we go. Or I should say, if I take this derivative, I get back to my dv. Okay, that's what I'm doing, is I'm checking to see if it did that. Okay, so uv, so that is 34t e to the 1/2 times 1/2 e to the 2t. Let me write this down like a human being. So this is times 1/2 e to the 2t. Okay, that's my v. Minus integral of v du. So this is 1/2 times 34 e to the 2t. Can we deal with the 1/2 times 34? Sure, that looks like 17 to me. Integral of e to the 2t. So this is 17 times 1/2 e to the 2t when I integrate this piece. Okay. Okay. This is dim dt here. Okay. Minus, and then we have 34 times 1/2, that's 17. Okay. T e to the 2t. And what are we doing here? We're going from 0 to 2, aren't we? So what are we going to do here? We are going to say at 2, so this is 17 times 2, right? That's my t. E to the 2 times 2, e to the 4, minus 17 halves, okay? E to the 4, minus, we can do this, okay? So minus, and then we have to put a 0 in. This piece here, this 0 here, is going to make the whole thing 0. Minus, and then we have 17 over 2, e to the 0, right? Which, what is e to the 0? E to the 0 is 1. Okay, so let's go ahead and figure this out. So we have 17 times 2, that's 34. E to the 4th minus 17 halves, e to the 4th plus 1. Because minus times a minus will be 17 halves. Okay, times 1. Right? So let's see here. How do they want their answer? Round to the nearest whole number. Okay. So let's plug this in. We have 34 times second function. This is e to the 4th. Okay. Minus 17 over 2 times e to the 4th plus, oops, let's get rid of that. Okay, plus 17 over 17 over 2. Okay, problem is e to the 4th is going to be a huge number. Okay, oh, look at that. So 14,000 or 1,401. Okay, 1,401. That's our nearest whole number, I believe. I'm really crossing my fingers over this because I have no idea what they're going to do with this. Okay, they're going to tell me I'm wrong regardless of what I type in. Okay, so we'll go ahead and check. Oops, I cleared it. 1401. Okay, let's see what we got here. No, come on. I think I can go up here and grab things and move them around. I didn't want to clear it. All right, check your answer. Fingers crossed. Hey, how about that? They actually believed me. All right. That was a surprise to me. So there is pretty much how we handle integration by parts. They're really not quite so bad. They can get bad if you especially if you do more than one, but these aren't too bad. Okay, so I wish you the best of luck with these. Please ask the questions, and you know, we can do these. All right. So don't be afraid to make the wrong guess. If it looks like it's running off the rails, or you're like, oh, I don't know what to do with this, don't be afraid to start again and make a new guess. Okay, just try to keep what you did before so that you can go back to the first one if the second one doesn't pan out. Okay. All right. So with that, I'm going to go ahead and let you go. I'll see you in the next video. Good luck, and I will see you later. All right. Good.